In previous videos, we have seen about the idea of work being the result of a force being applied to an object over a displacement. We've investigated that. We need to talk about a couple of other things before we can put all of these concepts together. So we're going to spend this video talking a little bit about energy, and then about a specific type of energy. So we've seen this word, we talked about it in a few previous videos. We all have an intuitive understanding of what energy is. We have the idea of this is the capacity to do things, right? If I need to go run a 5K, I need energy to do that. If I'm going to get out of bed in the morning, I need energy to do that. I usually get it with coffee. But energy is what makes my car go. It's what makes me go. It's what makes our world go. So we have an intuitive understanding of what energy is. For now, I think that's good. Most of us learned in grade school science that there are two types of energy. There is potential energy, which is stored energy. Think of a battery. A battery stores energy. You know, we'll talk about batteries in physics too. We definitely talk about them in terms of energy. We talk about them in other ways as well. But I can store energy in other places besides a battery. We've been talking about putting gasoline in cars and putting food in our bodies. Energy is stored in gasoline and food in the form of a chemical potential energy that I'm able to extract through chemical means. Nuclear power plants take advantage of energy stored inside atomic structures that I can get to by disassembling those structures. That would be nuclear potential energy. We're going to find energy stored in springs for spring potential energy, etc., etc. So there's all sorts of different forms of potential energy. There's a few that we deal with explicitly, the mechanical potential energies. We'll leave the chemical and nuclear to other classes. But in this case, we're not going to talk about potential energy just yet. We're going to talk about the other type of energy, energy of motion, usually called kinetic energy. Right? So potential energy is energy that's stored. Kinetic energy is energy that's being used, basically, is a good way to think about that. Kinetic energy is the energy that something has by virtue of being in motion. And as I said, there are all sorts of different types of potential energy, which leads to all sorts of different mathematical formulations of different types. But there's only one math formulation of kinetic energy. The symbol is K, and we define it as 1/2 mv squared, where m, of course, is the mass of the object in question. V squared, we're going to say, is the square of the speed. I can't say velocity. Number one, energy is not a vector, and velocity is. But if I have a velocity, how do I know what direction that is in? Well, chances are I'm using a negative or positive, right? And even if I'm not using it, there's something implicit in a vector, a velocity vector, that gives the direction that I lose when I square it. If I'm using a negative sign and I square it, I get a positive value out of that. We've seen something similar when we dealt with kinematic equations. But the idea is this is the square of the speed. I don't need to worry about the vector nature of it because energy is not a vector. Now, you got to be careful. We're going to see in a little bit that energy can move. And if it moves, then it clearly has some sort of direction. But when we talk about energy moving, we're not talking about a direction in space. We are usually talking about it moving from one object into another, or moving from some reservoir, like a battery or a spring, into another object. And for that, we don't worry about the direction in space. In fact, it doesn't even make a whole lot of sense. But we do worry about the direction if it's moving into an object or a system, or moving out of an object or a system. And so it has a direction, but it's not a spatial direction. So I'm going to leave off the vector notation. It's not a vector, is what I'm saying. It can be negative, it can be positive, again, because there is a direction associated with that. It's just not a spatial direction. So we'll have to define, what constitutes a positive movement of energy or a negative movement of energy, but that's easily done. All right, so this is the kinetic energy of an object, and there's really not much more to it than that. I do want to point out a few things. It is proportional to the mass, of course, but it is proportional to the square of the speed, which means if you double your mass, you get twice as much kinetic energy, but if you double your speed, you get 4 times as much kinetic energy because the speed gets squared. So be careful there, right? It depends on the mass, but not as much as it depends on the speed, if that makes sense. Unit-wise, what do we have here? Well, if I look at the units of mass, I get a kilogram. Units of speed are meters per second. If I square that, I get meters squared per second squared. Let me rewrite this a little bit differently. Kilogram, meter per second squared times a meter. No big deal, I just took one of these meters out of the numerator and put it off to the side. Well, what is this? We've seen this before as a Newton times a meter then. We've seen that in our discussion of work as a joule. All right, so I believe I mentioned in one of the previous videos that we can think of work as energy moving around. So maybe it makes sense, I hope it makes sense, that they have the same units. Energy has units of joules. That's the SI unit, right? English Standard has units of calories, which makes sense, right? You eat some food with a certain amount of calories. That's actually a measurement of the energy, although I think what they call a calorie in the food industry is actually what we would call a kilocalorie. I believe that's right. But at any rate, it's a measure of energy. There are other ways to do it. British thermal units is one. In the SI system, though, we're going to stick to joules or kilojoules or millijoules or insert whatever prefix you want to, but we're going to stick with joules as the unit of energy. So those are the units. Good. Well, okay, a couple of other things I want to point out. Kinetic energy can change, of course. Delta K is a thing. That is equal to, of course, K final minus K initial. As every delta is defined, final minus initial. If I go back up here and plug in the formula, and I furthermore make the assumption that my mass is not changing. Can my mass change? Absolutely. If you go on to do rocket science, you'll deal with masses that can change continuously as rockets burn up their fuel. When we do collisions, we're going to see that masses can change if 2 things stick together. But for now, let's let the mass stay the same and just assume that what's changing here is the speed. So, oops, sorry. If I keep hitting the stand, sorry. All right, if I do that, I'm gonna get 1/2 mv final squared, right? I'm letting my v change, not my mass, minus 1/2 mv initial squared. That is equal to 1/2 m v final squared minus v initial squared. And I'm pointing this out to caution you of a very common algebraic mistake. This is not equal to 1/2 m v final minus v initial quantity squared. No. And I'm sure most of you know this, but it's easy to forget when you're thinking about other things and just writing down solutions and trying to find your way through a lot of algebra. These are not the same thing. Right? You get cross terms in this. This is a binomial multiplication. There are no cross terms here. So be really careful. This is not the same thing as that. This is delta K, 1/2 m quantity v final squared minus v initial squared, end quantity. You can write it like this if you want to. But notice this can be positive or negative. If v final is less than v initial, then you get a negative value here. What does that mean? Well, think about what it means. If v final is less than v initial, that means you slowed down. Maybe you stopped. That means the final speed is less than the initial speed. That gives you a negative change in kinetic energy. What has to have happened? Well, some of this kinetic energy left the object. Right? Kinetic energy, it deals with masses and speeds. We're not letting the mass change. So if I slowed down, what that means is that kinetic energy is no longer in my object. or at least some of the kinetic energy is no longer in my object. We're going to find out later that it's not lost, it's somewhere, it went somewhere. But that's what I mean when I say negative and positive values of energy. A negative value is going to show you that the energy is leaving an object or a system of objects. A positive value, what would that mean? V final minus V initial. If V final is greater, that means the object or system of objects sped up, and that means my kinetic energy is, my change in kinetic energy is positive. That means that energy entered the object or system of objects. So hopefully we're getting an idea of what I mean when I talk about direction of energy and how positive and negative can relate to that. Of course, we're going to have to be really careful with how we define what constitutes a positive change and a negative change. But I will give you the punchline. If you have defined a system of objects, it could just be one object, it could be multiple objects, but if you have defined your system, if energy is going into the system, we call that a positive change with respect to the system. If energy leaves the system, we call that a negative change with respect to the system. One other caution, this is just kinetic energy. There are other ways that energy can enter and leave a system in the form of potential energy. So just because the energy content of a system changes, that actually doesn't necessarily mean that the kinetic energy changed. Think of the last time you put gas in your car or ate breakfast. While you're sitting at the gas pump, your kinetic energy doesn't change. But if you define the system as your car, then definitely the energy content changed because you put in gasoline. Now that's a little bit outside the scope here because we're restricting ourselves to mechanical energy, and that's chemical. But the idea is still the same. Just because my total energy content changes, it doesn't necessarily mean my kinetic energy changes. But very often, I'll find that to be the case. And in the next video, we're going to determine a specific relationship between the change in kinetic energy and the amount of energy that leaves or gets added to the system.